So before everybody starts bogging down the wireless connection, almost everything you need for this tutorial is on the VirtualBox in tutorial AlphaMelts, except for two things. One thing, really. There is an instruction file to lead you through the exercises, which I posted on the wiki last night. It's just a 4-page PDF or something, so it's just a few bytes. Shouldn't take long to get. There's also a copy of the PowerPoint that I'm going to show at the beginning of the tutorial, which I'm going to attempt to blow through at warp speed because I don't want to stand up here and talk. I want you guys to get calculating. But you'll have the PowerPoint to review at leisure later on. So everybody has the VirtualBox. And does everybody have the shared folder set up so they can actually extract files from the VirtualBox and look at them with useful things that run natively in your own operating system, like Microsoft Excel or whatever? Yeah? Okay. I think the VirtualBox includes some lightweight spreadsheet program, but it's probably easier to share out to the real world.
Is there any difference between version in the VirtualBox and the one on the Caltech website?
No. Well, actually, yes. The VirtualBox has version 1.3.2. Paula released version 1.4 today. The differences are trivial, though. They will not affect anything we do. Yeah. So I think you get version 1.4 if you do that. Actually, we'll see when we run it from the VirtualBox whether it notices that it's obsolete. That was one of my finest programming achievements 20 years ago, was working out the socket layer to get the program to check that it was whether it was obsolete or not. Come on. We may have reached critical mass on the wireless load. Does it matter whether you use KitP or KitPconf? No. They're both good. All right, I guess I'll get started. So what I want to do today is introduce you to the AlphaMelts software and explain what that is and how it relates to all the other melts softwares. Explain why you might want to use them and what they're good for, and how they're the same or different from other sorts of approaches to calculation of petrological phase equilibria, which is what this software does. So let's just start with a few logistical items. On the wiki, under tutorials, I've uploaded a PDF which says what the exercises we're going to be doing are. Okay. Also a copy of the PowerPoint that I'm going to show after I finish with logistics. Also a link to the complete manual for AlphaMelts, which documents every feature, every environment variable, every flag that you might want to set in exhaustive detail. And the download page. So once you're done with the VirtualBox, if you want to go on and run AlphaMelts in real life, that's where you can get it from. Okay, so that's there on the wiki. Okay. In the VirtualBox, within, obviously, tutorial, we have the AlphaMelts folder. Within the AlphaMelts folder, there are 3 directories. Linux AlphaMelts _1-3 is where the code and sort of the standard distribution that you would get when you download AlphaMelts lives. So what you see in this directory is the actual executable, 32-bit version, 64-bit version. You see some scripts which show up in green in this system. Run alphamelts.command is the master script that we're going to invoke to process our environment variable files, run the code, and then reprocess the output in a bunch of handy ways. There's a couple of other useful executables here. Fileformat.command will take any text file and it will reprocess the line endings to be the right format for your operating system. Right? So if you're going back and forth between Linux and Mac OS and Windows, text files are incompatible because of line endings, which is a horrible, annoying feature of operating systems. This will fix it for you wherever your text files came from. Also, columnpick.command is a Perl script that will take all of the output files generated by AlphaMelts, and you can identify exactly which columns you want from which files to reassemble into a single space-separated text file that you can then import into an Excel spreadsheet to do exactly what you want to do quickly without moving a lot of numbers around. Also here is another copy of the manual. There is the software brief where Paula Antashechkin and I originally announced AlphaMelts and what it's good for. And there's some default input files that set the environment variables and the bulk compositions. All that comes with the code whenever you download it. Okay. Within the directory alpha_nix are all of the files that we need for the exercises that we're going to do today. Okay? And those fall into 2 categories. There are .txt files, which are lists of environment variables and flags that we set to get the code to do what we want it to do, and .melts files, which set the bulk composition at which you're going to start the calculation. For every AlphaMelts run, you're going to need one of these settings files and one of these input files. Okay, so we'll get to those. Is everybody has the VirtualBox? Everybody can get to the wiki. Everybody has all of this setting up. So this is gorgeous. Usually when I do Melts short courses, we waste half our time on installation issues. Okay, so that's done. That's great. Yay. So let's go over to and talk quickly, I hope, about what melts and AlphaMelts are and why you might want to go about using them and what you can use them for. Okay. This is an interesting glitch. All right. What that slide says is talk back. You guys are good at that. We can skip it. All right. So what does melts do? In essence, it does the same thing that Hephaestus does. Okay? We had a long lecture from Lars about why you're going to want to use equilibrium thermodynamics to solve problems in Earth and planetary science. And we had an example of a code that solves this same problem. Given a bulk composition, expressed here as grams of oxides, okay, given 2 independent intensive parameters, such as pressure and temperature, or volume and temperature, or pressure and entropy, etc., and optionally given a constraint on the oxygen fugacity or the water activity, what you want to do is calculate thermodynamic equilibrium by finding that distribution of your bulk composition among all of the known phases, the phases being minerals, silicate liquid, and pure water vapor, that minimizes the thermodynamic potential. Okay? There is, in principle, a unique answer to that question. Okay? For any fixed closed system, if you specify two independent parameters, there is a unique solution that minimizes the Gibbs free energy. There may also be lots of local minima, but there's one global minimum. Okay? That's the core central calculation. But that's not always what you want to know. Just if I had this bulk composition at this pressure and temperature, what would the equilibrium state be? When you're doing petrology or geodynamics, you're often interested in following a path through thermodynamic space. Okay? And many of those paths are not actually equilibrium paths. For example, fractional crystallization. Right? As you're cooling the system, you're making crystals, you're taking them out. Okay? But fractional crystallization can be approximated as a series of equilibrium calculations with steps in between where you doctor the bulk composition by doing something like removing the solids. Same thing for fractional melting. Same thing for assimilation. Same thing for a lot of naturally important open system processes. You can break them down into steps. Find equilibrium, then change the system somehow and get new parameters and set the equilibrium, find the equilibrium again. Okay? So what's convenient about AlphaMelts is it takes that basic equilibrium calculation kernel, okay, and it makes it very straightforward to run it along a number of interesting paths to simulate natural processes, such as crystallization of a primary magma, either cooling at constant pressure or cooling at constant volume, or fractional processes or assimilation fractional processes, melting due to decompression at constant entropy, melting in the presence of assimilation. Lots of processes that we're interested in you can run without doing a lot of bookkeeping because the bookkeeping is automatic. Okay? So let's look at an example of such a problem. Okay? And that's fractionation of basalt. All right. Some of you will tune out right now and say, well, basalt is a rock. What does it tell me about the inner core, or what does it tell me about seismology? But go with me for a while, okay? Here's a whole pile of data. This is weight percent aluminum oxide versus weight percent magnesium oxide, and all of these are submarine glasses. The nice thing about a glass is there's only one good way to make it, which is quench a liquid. So if you see a composition here, and it's still glass, you know that there was a liquid of that composition, right? So these are samples of mid-ocean ridge basalt liquids, frozen as glass, so that we can recover them, bring them to our lab, and measure their compositions. Okay? And there's a great diversity of composition here, and the colors are hot pink for these specific rise, blue for the Mid-Atlantic Ridge, this darker purple for the Galapagos spreading center, and yellow triangles for the Lau Basin, which is a back arc spreading center. We would like to understand the origin of this diversity, right? What does this data mean? Why are there so many different glass compositions you can find on given mid-ocean ridges, and why are mid-ocean ridges different from one another, right? So we think, and this is a model because this has never actually been observed, we think the primary liquid that comes out of the mantle underneath oceanic crust is about here. Okay? It's higher in MgO than any glass that you can find erupted on the seafloor, and that's because they've all been processed in the oceanic crust. They have cooled, they have undergone some extent of fractional crystallization. Okay? So what you might want to do is model the crystallization of this primary liquid to see if the data can be mostly or partly explained by low pressure processes in the crust.
Where was that observed? Was that the melting inclusion, this primary liquid?
No, this is a model. You can find melt inclusions that get you most of the way back there.
Okay, so
but this is hypothetical. Okay? It's hypothetical in that if you fractionate olivine from this composition, you will get to the range of the most primitive glasses. And if you do melting calculations, this composition could be in equilibrium with the residual mantle. Right? Once you get back to liquids that are only fractionating olivine, it's still an ill-defined problem to say where was the primary liquid, but it's less ill-defined than if they're multiply saturated. Okay? So the first thing that happens when mantle-derived basalts get into the crust and start to cool is they saturate with olivine and they start crystallizing dunite. Okay? And if you're pulling out olivine, which is over here, then the liquid evolves that way. Right? At some point, they saturate with another mineral. Most mid-ocean ridge basalts saturate around 9% MgO with plagioclase, and they start to fractionate plagioclase plus olivine, which is a rock called a troctolite, and they evolve downwards in alumina versus MgO pretty steeply. It's pretty hard to see that in the data, okay? But we think it's there. We find those rocks from time to time. After a little while, it saturates with clinopyroxene, the third phase to come in, specifically augite, which is a high calcium clinopyroxene. And then for a long way, you fractionate gabbro. Gabbro is olivine plus plagioclase plus clinopyroxene. Its composition is over here somewhere, so the liquids evolve in this direction, which is, you see, the main principal component of variation amongst the mid-ocean ridge glasses. So they apparently are mostly explained by fractionation of gabbro, which makes up the oceanic lower crust, giving you progressively evolved liquids which can erupt at various points along that trend. And that's most of what goes on at most mid-ocean ridge crusts. Okay? There's also variation about that trend. It's not infinitely sharp. The data don't form a one-dimensional array. And there's still differences between different places that we haven't explained. The next thing that happens is that you saturate with an oxide phase, okay? And that drives you off in this direction to explain these highly evolved things, rhyolites really, that you can find on the Galapagos spreading center. Okay? Where this happens is sensitive to the oxygen fugacity, okay? Among other things. Yeah?
Does that mean all those law basin ones just are different oxygen fugacities that send it off the line, or they just higher scatter?
Something else.
Okay.
Something else. What's special about back arc basins? They're close to spreading center. They're close to trenches. Sediment affects the trace element geochemistry in a big way. What else comes off of slabs? Water. Yes, the story is all about water. Okay? So this is dry basalt fractionation. This is hydrous basalt fractionation. Okay? If I run a Melts calculation, what I just showed you now was hypothetical. Okay? If I actually run a Melts calculation with no water at all, I get this fractionation trend: olivine, troctolite, gabbro. If I add the amount of water that is actually present in normal mid-ocean ridge basalt glasses, then I get this trend, which goes right through the normal mid-ocean ridge data. Okay? If I add 0.8 weight% water, okay, and I fudge the initial alumina a little bit, I can get this fractionation trend, which goes through the Lau Basin data. Okay? So it's the effect of water. The effect of water is to suppress the crystallization of plagioclase to lower temperature later in the fractionation path. And that gives you higher alumina in the residual liquids because you're not taking out as much plagioclase. So this is one of the things that Melts can do. It can calculate the full fractionation path, the residual liquid as you're going along, the mineralogy at each point, and it can account for the effect of water, and it can account for the effect of FO2, and it can account for the effect of pressure, and you can explore all of those variables. Okay. This is the same thing plotted as FeO, total iron, FeO plus Fe2O3 versus MgO. Again, perfectly dry fractionation misses the data badly. You saturate with plagioclase too early, and you go up there.
That's because your initial amount of iron is too low?
No, it's simply because in the absence of water, plagioclase is too stable. And so it starts to crystallize there.
If you say it's 8%.
Oh, if I just lower the initial iron content down here, the problem is as I lower the iron content, I raise the magnesium number. And so to stay in equilibrium with the mantle, I actually have to move. I can't just move it down. I won't have a primitive liquid anymore. And even if I allow myself to play with the iron, the trend is too steep. So even if I start here, I'll move out of the data at some point. Okay? On top of which, when you actually pick up these glasses, they do have water in them, right? So dry fractionation is only a useful model if you only have models that don't account for water. Okay? So with the amounts of water that you actually see in normal morbs, you can reproduce the tholeiitic fractionation trend with the right amount of iron enrichment. You can saturate with oxide in the right place, and you can head off towards these weirdo rhyolites that you find in Galapagos. And again, if you add water, a lot of water, you can reproduce the back arc fractionation trend. Okay? So I consider this to be a remarkable success of the thermodynamic model. Okay? It really reproduces what is going on amongst various mid-ocean ridges and the systematics on a given mid-ocean ridge. You don't have to believe that what actually happens underneath a mid-ocean ridge is perfect isobaric fractional crystallization at buffered oxygen fugacity, but it appears to be a really good model. It explains the variations amongst the data. Okay. Let's skip that. Okay, so that's one thing we can do with the code. We can fractionate basalt and other magmatic liquids to relate them to each other so that, for example, if you only have evolved liquids, you can still try to say something about the primary processes in the mantle that were responsible for generating those liquids. You can correct for fractionation. Okay? You can test for whether suites of liquids are related to each other by fractionation or whether there's some other kind of heterogeneity going on. That's an extremely useful thing to be able to do. Okay? The code can do many other things because thermodynamics is a very powerful theory. Here is from some completely different part of parameter space, okay? An experiment that Craig Lundstrom did, the dots connected by the wiggly red line, okay? This was a two-liquid diffusion experiment, okay? A liquid initially rich in sodium and poor in silica, a basanite, was placed in contact with the liquid initially poor in sodium and rich in silica, a tholeite, okay? And they were allowed to interdiffuse for a few minutes at high temperature. The sodium profile that came out has this curious double-humped shape, which is the signature of uphill diffusion. Sodium moving, at least locally, against its own concentration gradient. This is a thing that can happen in multi-component systems. Okay? The traditional way to analyze this is to generalize from a diffusion coefficient to a diffusion matrix. Okay, where you can have a D for motion of sodium driven by gradients in silicon concentration and a D for motion of sodium driven by gradients in sodium concentration. Okay? Two parameters to explain the sodium profile. If you're also trying to explain the silicon profile, 4 parameters. Okay? But the main reason for uphill diffusion is that components in liquids and multi-component solutions do not actually go down concentration gradients. They go down chemical potential gradients in order to minimize the free energy of the system. And if you know the thermodynamics of the liquid solution, you can take your concentrations and you can convert them to chemical potentials. And what you find in this case is that the sodium is actually going down its own chemical potential gradient according to the Melts model everywhere in the system. And therefore, you can fit the diffusion with one parameter, just the rate at which sodium goes down its own chemical potential gradient. And so the green fit, which is no worse than the blue fit, neither of which really fit the data because this diffusion couple was not long enough to actually be a semi-infinite diffusion couple, which is the way it's been modeled. Okay? With one parameter, you can fit the data just as well as you can with 4 parameters, okay, if you don't use the thermodynamic information. So this is just meant to be another case where if you have a thermodynamic model of silicate liquids, you can do some interesting science. Okay? One more example, motivational example of something you can do with this model. Okay? And now we're getting into the mantle. This is looking at the residual mineralogy of peridotite during decompression melting. Okay? So in this case, this should say kilobars, sorry, not bars. Okay? We have a peridotite initially at the solidus at, let's say, 1.8 or so GPa, okay? And it's a nice, regular old fertile lertzolite. It's got about 50% olivine, okay? If you do fractional melting and decompress this thing, as it melts, the amount of olivine goes up, okay? And you will end up, if you go all the way to 1 bar, with a Harzbergite that's got about, 77% olivine. It's still got residual orthopyroxene in it. What is observed in ophiolites that sample the suboceanic mantle lithosphere is there are veins of dunite, of pure olivine rock, which are thought to be the conduits through which melt has been extracted through the shallow upper mantle, right? But how do you make dunite? How do you get rid of orthopyroxene? If you just melt the rock, you never lose the orthopyroxene. You still have about 20% orthopyroxene. Okay? The way it's thought to happen is by focused flow. So when extra melt from deep in the mantle comes through conduits containing peridotite at low pressure, it reacts with those conduits in such a way as to dissolve the orthopyroxene, crystallize a little olivine, but actually increase the melt fraction, increase the permeability, and give you an instability that makes these channels run away. And this is a process that's been well studied dynamically. And this is what it looks like in a simulation in the MELTS model. Okay? If I take my column where I'm doing decompression melting, and I start at each step adding extra melt to the column as if it had been extracted from adjacent columns, okay, and running it through my column at equilibrium, I see that I get a more rapid increase in the percentage of olivine in the mode. And in fact, I can get to a basically pure olivine rock. There's just a couple of percent of spinel. That's a dunite. Okay? At low pressure. It's actually quite hard to explain formation of dunite at 1 GPa, which is where the Peter Kellerman's school of thought about mid-ocean ridges would like it to happen. You need a lot of melt flux or a pretty high potential temperature. But that's a process we can simulate. And all of the bookkeeping of doing this decompression melting, of focusing the melt into the column, of keeping track of the residue, it's all automated in AlphaMelts. So I was actually somewhat horrified to see a recent manuscript by Henry Dick where, using the old version of MELTS, he did this all by hand, taking the output from each step over to a spreadsheet, recalculating and putting it back in. I wish he'd known about AlphaMelts. He would have saved several hundred hours of his time. Okay. So let's talk about what the MELTS programs do. Okay. If we want to solve our general problem of minimizing free energy, okay, we need three things. We need a model that tells us what's the Gibbs free energy as a function of pressure, temperature, and composition, and all of its derivatives for every phase we might be interested in. Same as Hephaesto, except we have one really important extra phase here, which is silicate liquid, which Hephaesto does not include. Also, we have considerably more detailed models of highly multi-component phases like the pyroxenes that we care about in the crust that have sodium and titanium and ferric iron in them. Okay? You need algorithms, principally the central algorithm to find your minimum, but also ancillary algorithms to do things like decide when you're going to add a phase to the system, when you're going to remove a phase, when you're going to split a phase into two coexisting examples, okay? And when you want to do something like fractionate the melt or assimilate a solid or focus more melt into the system, okay, or adjust the FO2, you need extra algorithms to do all that. And then you need an interface. You need something that allows you, a human, to talk to all of this in a hopefully convenient way, get your problem in, get your data out. Okay? So there are really only one set of algorithms for the whole MELTS world. Okay? There are, at this point, three subdivisions of the model that are called MELTS, P-MELTS, and rhyolite melts. Okay? Published respectively in 1996, 2002, and 2012. Okay? Melts and rhyolite melts are best for low-pressure crustal problems. Rhyolite melts is a tweak that makes it work for granites. It's the same as melts for basalts. P-melts is a recalibration that does better at high pressure and is the right one to use for melting of the mantle from about 1 to about 3 GPa. What you're supposed to do at half a GPa is not clear. What you should do if you need to go past 3 GPa is hopefully you don't. Okay? We'll be building better higher pressure models later as we go. Okay? So we'll both do MELTS calculations and P-MELTS calculations today. There are about 4 interfaces at this point. There's the original graphical user interface, the blue box that Mark Yorso wrote back in '96. It's most convenient for some people, but it's somewhat limiting. It can only do the calculations that Mark thought of that you might want to do. And also, I find the output files very inflexible. So when I started doing, I got the code so I could hack into underneath the graphical user interface, and I started making up lots of other calculations you might want to do. I assembled them into the AlphaMelts front end so that everybody else could do some of these more interesting calculations. So AlphaMelts is a totally menu-driven, text-only, file in, file out approach to this problem. There's no pretty interface, but it's more flexible, and it has the advantage that Paula and I will add new features quickly if you ask for them, which is not true of the graphical user interface. It evolves very, very slowly. There's also now AlphaMelts, which is an Excel front end that Gil Gualda wrote, which allows you to query through the web and do all the calculations at Mark Giorso's server and just see the output back in your spreadsheet. Still somewhat limited functionality, but it's out there. And we are close to releasing what we call libAlphaMelts, which is a set of libraries that you can call from MATLAB or from Sitcom or from any environment that you are interested in to get equilibrium results back into your favorite large-scale dynamical code. Okay? But today we're just going to do AlphaMelts calculations. Let's talk quickly about what the Melts model is. Okay? It is originally intended for igneous petrology. I have extended it to work below the solidus so it can do a little bit of metamorphic petrology. So it includes a self-consistent set of standard state properties for lots of pure solids and end members of solid solutions, for pure water vapor, and for silicate liquid, accounting for this list of oxide components, which is a pretty long list. You don't always have all of these components, but if you're interested in natural silicate liquids, okay, that you can measure with a microprobe and try to understand, you're going to be interested usually in silica, TiO2, Al2O3, iron at some redox state, maybe chromium, maybe manganese, magnesium, calcium, sodium, potassium, maybe phosphorus, maybe water, right? Usually we have 10 to 12 oxides running around that we care about. So these are much more complicated systems than the 3, 4, 5, 6 component systems that we use as models for deep mantle processes. The model includes solid solution models for a number of interesting phases like feldspars, pyroxenes, olivines, amphibols, sort of spinels, garnets, okay, that account for the complexity of thermodynamics of solid solutions, which principally comes from, in many cases, the abundance of different mineralogical sites and the ability of cations to substitute onto more than one site, which leads to ordering phenomena, which affects the entropy, which you'd better get right or you're not going to have the right model. Okay. Perhaps the core of melts is something that Giorso and Carmichael introduced all the way back in 1983. It is the, how shall I put it? The simplest model of the mixing properties of silicate liquids that is capable of explaining the data for natural compositions, but that can also have a small enough number of parameters that you might be able to calibrate them all. Okay? And that is something called an expanded regular solution model, which I will talk about in a moment, calibrated to a large database of experimental petrology results. Okay? So PMelts just adds a bunch more high-pressure data, so it works better for mantle processes. It actually works worse for low-pressure processes. This is a result of the simplifications that go into the construction of the model. The model is forced to compromise between high-pressure data and low-pressure data because it can't actually fit them all at once. So when you put in more high-pressure data, the fit at low pressure got a little bit worse. Okay? pHmelts is a 2004 update to PMelts that accounts for the way water behaves in the Earth's upper mantle. Okay? We think there's a couple, let's say 1 to 200 parts per million water in typical upper mantle rocks. It is not present as a hydrous phase. It is present as defects in the nominally anhydrous minerals. Of course, this affects the physical properties, the viscosity, and the seismic velocities, but it also strongly affects the melting behavior. And it affects the melting behavior in a way that you cannot really calculate unless you account for the way the water leaks out of the anhydrous minerals into the liquid. Okay? So pHmelts is an accounting trick that couples a trace element reservoir of water to the liquid, which is the only major phase where the thermodynamics of water are correctly accounted for. But it allows you to actually describe water undersaturated melting of slightly hydrous peridotite, which is very handy. When I wrote pHmelts, I also put in a general purpose trace element engine where you can specify, or the code will specify for you, partition coefficients of any element in the periodic table. and they will be passively tracked through the code. So if you're doing equilibrium melting or disequilibrium melting or fractional crystallization, the trace elements aren't affecting the calculation, but it's sometimes nice to know what prediction the calculation makes for where the trace elements are going. Okay? Just as an example of a pH melts result, this is temperature versus pressure. This is the Workman and Hart depleted Morb mantle peridotite. This is the dry solidus. Okay, so above here we have some liquid in the absence of water. Below here we have no liquid. You'll see it has a somewhat unusual shape that you might not have intuited, since it's usually drawn as a straight line that starts at 1100 degrees and goes up with a constant slope. Okay? The shape is the result of the thermodynamics. In particular, this kink here is the result of the plagioclase to spinel lertzolite phase transition. And the downward curvature is the result of the fact that silicate liquids are more compressible than solids, so the volume of fusion goes down with increasing pressure, so the slopes of these things get lower. And what you see here below the dry solidus is the water-saturated solidus, and contours for the location of the solidus as a function of water content, or in blue, water activity. Okay? And so according to this model, let's say 300 parts per million water should depress the beginning of melting, let's say on the 1350 degree C potential temperature isentrope, from about 1.8 GPa to about 2.5 GPa or something like that.
Well,
Yeah?
you said that PMET was not as good at low pressure than MET.
Yes.
But if you want to have water in the system, that you have to use HMET.
Yes.
Right?
So
It
can be H melts. You don't need.
HMET?
Yeah.
Okay.
The H trick works with either P or not P.
Okay.
Yes. But you generally don't need it because at low pressure there's really not very much water in the anhydrous minerals. And melts without the H trick already knows how to deal with water in the liquid. Okay. So rhyolite melts is very new. It's a small adjustment that allows it to get the right answer for granites. Okay, here's a beautiful slide for you to refer to later. These are all of the solid solutions that are in melts, okay, and all of their components. The granddaddy is the 7-component pyroxene model. Okay? Plus there's a whole bunch of pure phases. They're all there. Okay? The things that are not there, and that's worth spending a little time on, okay, are certain minor components in pyroxene that matter for very high pressure. Okay? Certain minor components in garnet, or major components in garnet, that matter for very high pressure if you're going to go to the transition zone. If you want to do real, let's say, subduction phase equilibria, the mica models that are in there are not really good enough for high pressure because they don't include fengite. Amphiboles are insane. Okay? To do amphibole as well as we have done pyroxene would require 55 chemical end members and mixing on 11 sites, and the complexity of calibrating these models goes up as the cube of the number of components plus the number of sites. So there are several simplified amphibole models in there, but they're really lousy. So if you are trying to describe amphiboles, you're probably out of luck. The only component that we include in the vapor phase right now is water. Okay, so we don't do water-CO2 mixtures, sorry, yet. And we don't account for the ability of water vapor under supercritical conditions to transport lots of other things. We don't do carbonates. We don't do accessory phases. We don't do really low temperature minerals. There's some things that are missing because it was really meant to be originally an igneous petrology code that can now go some distance below the solidus. Okay. I'm just going to leave this in here for you guys to review at your leisure if you want to know what the free energy models underlying the model are and how they were calibrated. Okay. Because I want to get to actually doing the calculations and have enough time to get somewhere. Okay? So like I said, we're going to use AlphaMelts today, but there's also the graphical user interface version, the Excel spreadsheet. There's an app on the Mac App Store called PhasePlot that just makes little PT grids of pie diagrams of phase assemblages that sometimes is a handy thing to do. Okay? Not all of these front ends run or are supported on all operating systems, and this gets confusing quickly. Okay, but AlphaMelts is supported for Mac, Windows, and Linux, and that's one of the reasons you might want to use it. It's the only supported version for Windows. Although looking around, it's mostly a Mac crowd. Okay. Burning questions about what the model is before we jump into actually using it. I know I went really quickly through what it is because I could spend all week on it, and we don't have that much time. Okay? Good. So, in the virtual box, okay, in the AlphaNix folder, the first exercise that I want to do is fractional crystallization. Okay? So let's look at the file fractional_crystallization.txt. Okay? The AlphaMelts program, its behavior is determined by a list of environment variables that are in these text files that will be read in by the Perl wrapper and fed to the executable. Okay? There are lots of them. They are fully documented in the manual. So the meaning of every one of them is knowable. But let's just look at the really important ones. First important one, AlphaMelts version. This can be melts or pmelts. Those are the only legal choices here. Okay, phmelts will be turned on somewhere else. Rhyolite melts is not yet included in the AlphaMelts code. It will be soon. Okay, so this is going to be a melts calculation because this is low pressure fractional crystallization of the basalt in the crust. Okay, Celsius output is handy for some people. If you don't define that, you'll get Kelvin. Okay, AlphaMelts mode. Okay, this one is important. This really determines what kind of calculation you're doing. These are your choices. Okay, we're going to do isobaric, meaning we're going to keep the pressure constant, and as we iterate through progressive calculations, we're going to change the temperature. Okay? The amount by which we are going to change the temperature is set by AlphaMelts delta T, which is set to -1 degree. Okay? The code is so fast that there's no reason not to use a fine grid like a degree. Okay? You see bounds on the pressure and bounds on the temperature. These will stop the code for you if you let it. Okay? Or you can let it run until it crashes if you go beyond the reasonable bounds. Okay? So you always need to worry what version you're running, what mode you're in, and what pressure or temperature steps you're using. Just about always need to know that. Okay? All right, here's another important flag. Adiabat fractionate solids. We want to do fractional crystallization, so we turn that on. That means that at the end of every calculation, if there are any solid minerals in the assemblage, they're going to be removed. And we will get a new bulk composition from which those solids have been extracted, updating major and trace element compositions and the energy and all the other variables. Okay? If you don't set that, then you're going to get equilibrium crystallization where the system is closed, constant mass, constant composition throughout the calculation. Okay? We're not going to turn on the trace element engine yet, so don't worry about it. Okay? These two here are sometimes worth worrying about. You'll see when we run the code that there's a menu option to do a single calculation and return. And sometimes when you're setting things up, you explore a bunch of single calculations before you say, run the full path. Okay? If you turn on AlphaMelts save all, then all of those single calculations will be included in the output files. If you don't, the output files will only show the path that you get once you start on the full calculation. AlphaMelts skip failure also is an extremely helpful one. The code is not globally convergent. You can crash it. You probably will crash it today. If you're doing some long series of calculations, sometimes when it crashes you want to stop, and sometimes you want to skip that one and keep going. So this will allow you to skip and keep going, right? There are a bunch of things that you can set either here in the setup file or in the input file that we will look at next, or interactively from the menu. Okay? I tend to set them in the composition file, so I have them commented out here. Okay? But you can set them up. Everything that's commented out is ignored. One warning that I should give you about setting environment variables, okay? In many cases, they are tested for whether they are defined or not defined. The value to which you set them is ignored if they are flags. So for example, if I set AlphaMelts fractionate solids to the value false, it's true because I set it, right? Does that make sense? If you don't want it, don't set it. If it's set, it doesn't matter what value you set it to. It just tests in some cases for whether a variable is null or not null. If I don't set it, it's null. If I set it, it's not null, and it doesn't matter what I set it to. So I could set it to true or false. It would still act like it's true. I'm just warning you that's one of those things that could screw you up. Okay? Okay, let's look at... Yeah, if they're commented out, then they're going to be null. Let's look at the composition file morb-fo2.melts. Okay? You always need, when you're running AlphaMelts, an input file to define your composition. There isn't any interactive way to put it in like there is in the graphical user interface. This is a good example of the format of these files. They're ordinary text files. There are certain lines that you're allowed to define, like title, initial composition, name of an oxide, grams of that oxide. Okay? These could be weight percent if you want, but they're really grams, an extensive quantity that happen to add to 100 in this case, but they don't have to. Okay? Initial temperature will be read by the code. Initial pressure will be read by the code. These others, final temperature, pressure, increment, dPdt, those are ignored. Those are holdovers from the old version of melts. Okay? So we're defining our composition. Those of you who are petrologists or who are used to playing with basalts will notice that this is a reasonably primitive basalt glass with 9% MgO. Okay? And 0.28% water. It's an NMORB. Okay? This one down at the bottom is important. Log FO2 path. Okay? You have two options in all melts calculations. You can run them as a closed system where you set up some amount of ferric iron and some amount of ferrous iron, and those are independently conserved species throughout the calculation. Okay? It will then calculate and tell you what oxygen fugacity you are at as the code runs. Or you can turn on an FO2 buffer. Okay? And now the system becomes open to exchange of oxygen with the environment. It will drive along an FO2 buffer, and the way that it does that is it converts some ferrous iron to ferric iron or back in order to stay on the FO2 buffer that you want. Okay? For basalt fractionation, if I run closed system, I will go off in a totally crazy direction. Okay? Because the oxygen fugacity really matters during fractional crystallization. It's the main reason why mid-ocean ridges evolve differently from subduction zones. And if we want this to follow a tholeiitic fractionation trend, we're going to buffer it to the phaolite magnetite quartz buffer. Okay? So that's all that's in our input file. Okay, so I think for this calculation, which I want you all to now go and do, you're going to need those two input files, and you don't have to edit them at all. You just are going to use them as is. Okay? So to run the calculation, we use the script run alphamelts.command, which your VirtualBox has already set up the path correctly, so you don't have to type / or // blah, blah, blah. It's just going to run. Okay? And we're going to use two command line flags, although you don't have to use them. It'll ask you for them if you don't put them in. The first is -f, and we will tell it which of those setup files we want it to use. Okay? So it's going to read the environment variables from fractionalcrystallization.txt. Okay? The second one tells it where to put the output. Because like Hephaesto, except not quite as bad because the output files have meaningful names, not fort.58, fort.66, and fort.92. Okay. Nevertheless, the output files from every calculation have the same name, and they will overwrite each other unless you put them somewhere sensible and keep track. Okay, so -p will create a directory, or if the directory is already there, we'll use it. We'll put our output files there. Okay. You can also, at this point, if you are doing a calculation you have done before, you can tell it to read in a batch file, which will be simply a list of the menu commands that we are about to put in interactively, and it will pipe them through to the code, and the whole code will run without you having to sit there and type. Okay, not going to do that today, but that's extremely handy. Yeah, and that would be dash B. So I said go, and it went. Okay. So when you start it, it spews a bunch of stuff at you. I'm trying to get it to scroll back up. There we go. Okay, so when you start it, okay, first it echoes back the information that it got from the setup file. Okay, if you don't see that, you didn't correctly tell it which setup file to look at, right? So it echoes back to us that we're doing an isobaric fractional crystallization calculation with melts, with a time step, with a temperature step of 1 degree. Okay? It checks the web for updates, and it will tell you if you're running an obsolete version. Okay? Then it spews a bunch of obnoxious stuff at you about how to cite the model before you publish it from it. Okay? And then it gives you the menu. Okay? And the menu is fairly long and clunky at this point, but we're going to go through it in sort of a sensible order. The first thing you always do, you can't do anything until you do this, is option 1, read a melts file to set the composition of the system. Okay? So, option 1, the file we're going to use is morb fo2.melts. Was it a capital M? I don't remember. We'll find out now. No. It echoes back to you the composition that it read in. If it doesn't echo back to you the composition, you didn't type the file name correctly. Okay? And it brings you back to the menu. But now it knows the bulk composition. Okay? The next option you might want is number 2, okay, which is to set the pressure and temperature. Okay? But we don't have to because those were in the input file already. Right? So we'll go right on down to number 3, a single batch calculation. Okay? So it's actually going to do an equilibrium. And now we come to an interesting issue, which is what are we going to use for the initial guess? Okay? All downhill minimization programs for constrained optimization have to start from some starting point that satisfies the constraints. And then it can search the null space, as we heard repeatedly, for other better states that satisfy the constraints. But you got to start somewhere. Okay? And we have 2 ways to do it. One is the superliquidus initial guess, and this is always available to you. The liquid has complete compositional freedom. It spans the space. So you can always guess that you are above the liquidus and you have a system that is pure liquid and the liquid is equal in composition to the bulk. That's always available to you. Okay? Sometimes, though, that's really clunky because you're working below or near the solidus and you don't want to waste the time to find all of the solids and work your way all the way down. So we have an alternative initial guess called the subsolidus initial guess. Okay? And what this does is a norm calculation, not the CIPW norm, but a different norm calculation that remaps your bulk composition into a guess of mineral components and allows you to start the code. And we'll do that later, but for now, we're going to do a superliquidus initial guess because we're close to the liquidus. So I said number 1 and go. And it went. And it says, okay, at P1000 bars, all pressures are in bars, at a temperature of 1228.12 degrees C, we have 100.4 grams of liquid with this composition. We have an activity of water of 0.01. We have a melt fraction of almost 1. And we have a trace of spinel. And this is the formula of our spinel, which is mostly magnesium, aluminum, some chromium. Okay, it's a true spinel. So that was an example of a calculation. Okay? Now, when you're doing fractional crystallization, you want to start near the liquidus. Okay? So we could start there, or just to be really anal about it, we might want to literally start above the liquidus. So I'll say, number 2, change the starting or continuation parameters. I'm going to increase the temperature by 1 degree from 1228.12 to 1229.12. Okay? I'm going to leave the pressure alone, so I can, these pressure and temperature dialogues always allow you to say 0 just to keep the old number, so you don't have to retype it, because 0 is not a legal pressure or temperature, okay, in this case. And we'll run again. This time it's not going to ask me superliquidus or subsolidus because it already has an initial guess from the previous solution. So it runs, and it dropped the phase spinel from the assemblage. It added it back, just checking, dropped it again, and it returned an equilibrium solution that is all liquid. So this is a good initial guess for a fractional melting run. Okay? Now, there's a bunch of other stuff we could do here, but for this calculation, we don't need any of it. We can say, number 4, execute. Okay? So what that means is, since we've set up an isobaric calculation with -1 degree temperature steps, it's going to iterate. It's going to do the calculation. It's going to lower it 1 degree. It's going to do it again. It's going to lower it 1 degree. And it's going to keep going until either it crashes or it gets to some bound. And we have AlphaMelts min T set to 1,000 degrees. So it's going to do 229 steps. Okay? Execute. Boom, 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 boom. It's very fast. Okay? This is an easy calculation for it. You see it going so fast you can't possibly follow what's going on. Okay? You see it come right down to 1,000 degrees and return. Okay? And what did we get to? We started with 100 grams of liquid that was about 49% silica and 9% MgO, okay, and 0.28% water. We ended up with 11 grams of liquid, which is no longer basalt. It's, well, what would you call 61% silica? Dacite? Andesite, maybe? Okay? So it became more evolved. Hey, that's what fractional crystallization should do. Okay? We did not saturate with water, although the water activity went up from 0.01 to 0.3 something. Okay? You'll note that the melt fraction reported here is still almost 1. Okay? Because that number is the melt fraction of the current assemblage from which all the fractionated solids have been removed all the way along. And so all you see here is the last increment of crystallization in that last degree. Just a little bit of each of these solid phases came out. Okay? So that's the whole thing for running a fractional crystallization calculation. Okay? We started the code. When we started it, it read the settings file with the environment variable flags. We read in a composition. We checked our starting conditions. We did a single calculation to make sure that we were in a good place. We adjusted a little bit. And then we executed it. It ran the whole sequence, and it returned to the menu. Okay? Now, we could write out some output files here, but we don't need to because it happens automatically, so you don't lose this output even if you crash or if you exit without saving anything. Okay? So we'll just quit. Okay? When we quit, we see the output directory that we asked for. Right? And if we look in the output directory, we see 8 output files. Okay? All of them _table.txt format. These are all space-separated text files. Okay? They're all easy to import into the spreadsheet of your choice, or you can process them through column pick to get particular combinations of variables that you want. AlphaMelts table.txt includes all the output in a single file, which makes it less convenient for importing into spreadsheets. Okay? Liquid composition will show the liquid composition for every step that we did. Okay? Let's just look at some of these. Okay? So I already exported them over here to Excel just to save us a little bit of time. Okay? System main table.txt shows for every step of the calculation that we did, pressure, temperature in degrees C, because we asked for that, the mass of the system, the melt fraction of the current system by mass, which stays close to 1 because this is fractional crystallization. Okay, but you see the mass going down because we're removing mass, the melt fraction by volume, the total entropy in units of joules per Kelvin. So this is an extensive quantity, right? It's joules per Kelvin per 100.4 grams. The enthalpy, also an extensive quantity in joules. The volume in cubic centimeters. The heat capacity in joules per Kelvin. the compressibility, the thermal expansion coefficient, the oxygen fugacity in absolute units, log 10 FO2, the oxygen fugacity relative to the buffer, we said fix it to QFM, so those are all zeros, as they should be. The density of the liquid in grams per cubic centimeter, the density of the solid in grams per cubic centimeter, the viscosity of the liquid in log 10 poise from the Shaw model, which is somewhat out of fashion, but it gives you some sort of number, the activity of water, and the chi-squared, which doesn't mean anything because we're not doing a fitting calculation. Okay? And so there's an entry there for every one of those variables for every temperature step that we did, all the way down to 1,000 degrees. Okay? Let's look next at phase mass table.txt. Okay? Very handy table. It shows you for each calculation that we did the total mass of the system and the mass in grams of each of the phases. Okay? And there'll be an entry for any phase that appeared at any step of the calculation. So we see liquid. The first thing that crystallized was spinel. The second thing that crystallized was feldspar. That went on for about 8 degrees. Then spinel stopped crystallizing and olivine started crystallizing. That went on for about 15 degrees. Then a clinopyroxene started to crystallize. Then spinel came back in. That went on for a long way. So this is Gabbro fractionation. Olivine plus augite plus feldspar plus spinel. That went on for a long time. That went on for a long time. Oh, and then what happened here? At 1112 degrees C, olivine stopped crystallizing. And you can't see the column header, but it says clinopyroxene 1, just the second clinopyroxene counting from 0, started to crystallize. Okay? And that went on for some time. Okay? This is an event that is of interest to petrologists during fractional crystallization of basalts. At some point, you stop crystallizing olivine and you start crystallizing low calcium clinopyroxene, right? Or orthopyroxene, depending on where you are. So this is pigeonite over here. And that went on for a while. That went on for a while. Eventually, we saturated with phosphate. And when we get down to 1,000 degrees, we're still crystallizing no olivine, sorry, 2 pyroxenes, feldspar, spinel, and apatite. We can look at liquid composition. Okay? For every composition, every temperature that we did, we see the mass of liquid. We see the composition of the liquid in weight % oxides. Okay? I've tacked on here a useful calculation, which is total iron. Okay? And here's a handy, approximate, but unreasonably accurate formula. Total iron as FeO is FeO plus 0.9 times Fe2O3. It's actually like 0.8999. It's unreasonably precise. Okay? So sometimes you care about total iron. Sometimes you care separately about FeO and Fe2O3. Okay? And just for fun, I have graphed them up. Okay? So you can see what happens. We're going from originally 9.1% MgO. Okay? I haven't labeled these things, but this one is iron. Silica's up there somewhere. When we fractionate, we crystallize just feldspar at first, and the MgO goes up a little bit. Then we add olivine, and it goes down. And some components are incompatible, and they accumulate. Some components are compatible, and they go down. If you're a petrologist and you care about the details of the behavior of different oxides, you can look through here and decide whether you think that they all make sense or not. Okay? But it's all there. And in phase main table.txt, not just for liquid, but for every solid phase, there is an entry here that shows you, for every calculation where olivine was present, for example, the pressure, the temperature, the mass of olivine, the entropy, enthalpy, volume, and heat capacity of olivine, the molar formula of the olivine, and the composition of the olivine and weight percent oxides. Okay? So this particular calculation, when it first crystallized olivine with Forsterite 87. So that's pretty primitive. And it ran, as we went, down to Forsterite 71 before it stopped crystallizing olivine. Also, if we look at feldspar, that's spinel. Oh, if we look at spinel, actually, for those of you who are mineralogists or petrologists, the first spinel was mostly magnesium and aluminum with some chromium. So that's spinel in the strict sense. But as we went along, the composition evolved until by the time we get down here at low temperature, it's mostly Fe2 plus and Fe3 plus, and some titanium. Now it's magnetite. Right? And the feldspar, when it first came in at the liquidus, was AN82. And by the time we were done, it is AN35, so normally zoned plagioclase. So the perfectly reasonable fractionation behavior for basalt. Okay, so you have all those output files now. You could play with them at leisure. You can see all of the wonderful details. You could go and match them to data. Let's go back and look at a different kind of calculation, unless there's questions about how I pulled all of that off. Okay. Should I stop talking and let you guys do the calculations? Or should I just keep doing them in real time, and hopefully you're doing them along with me?
Can I ask you a question? So
Yeah.
The residual solid,
Yeah.
right? The composition is in solid.com. Does it also give the phases that are of the residuum?
So all that information is present. Phase mass shows you the masses of the phases. Phase main shows you the composition of each phase and the mass of the phases. Solid comp will just show you the bulk composition of the residual solids. Okay, and for melting, it's residual solids. For crystallization, it's each increment of crystallization before we yank it out of the system. Okay, is what you would see in that table. So all that information is there, so maybe distributed between different files, but hopefully in all the forms that you might want it in. Okay, so example 2 is a different calculation. What we did in example 1 was we started with a reasonably primitive liquid, and we cooled it, doing a forward model of fractional crystallization, right? That's what you might do if you have a suite of data that includes a relatively primitive composition, and you want to test the hypothesis that your other compositions are descended from it. But what we often try to do is say we have only evolved compositions, and we would like to infer what the primitive or primary composition they came from was. Okay? If the glasses that you have, the most primitive glasses you have, are multiply saturated, if they're already fractionating both olivine and plagioclase, or olivine, plagioclase, and clinopyroxene, which is almost always going to be true in an arc volcano, and it's usually going to be true at a mid-ocean ridge volcano. The only time you're going to usually find really primitive glasses is if you're very lucky, or if you have melt inclusions, or if you're at some very hot place like Iceland or Baffin Island or Ontong Java or whatever. Okay? If you have a multiply saturated liquid, reversing the process of fractionation to find the primary liquid is an ill-defined problem. Because during fractionation, you start crystallizing, let's say, olivine. Then you start crystallizing olivine plus plagioclase, and you come on to a cotectic. And once you have a cotectic glass, it has lost any memory of which side of the cotectic it came from. It doesn't know anymore whether it first crystallized plagioclase or first crystallized olivine. That information is gone. Okay? But if you have a liquid which is only saturated with olivine, it is a better defined problem to find the liquidus, see the composition of olivine that is in equilibrium with your glass, add some back in, mix it, find the new higher temperature liquidus, find the composition of olivine that's in equilibrium with that more primitive glass, add some of it in, mix it, raise the temperature again and go back along the olivine control line. And the usual way this is done is you go back until you're in equilibrium with what you think is the magnesium content or the magnesium number of the residual olivine. Maybe you go back to the most primitive olivine you can find in the area. Maybe you go back to Forsterite 90 because that's just what you think residual peridotite look like. Maybe you use the Hertzberg and O'Hara PriMelt2 model to go back to something that could be a primary melt of peridotite. In any case, the next calculation we're going to do is reverse fractionation. Okay? We're going to automate the process of finding the liquidus, adding an increment of the liquidus phase, going up temperature, and continuing until we reach some target. Okay? So we're going to look at...
How do you know that the phase that you need to add is only olivine? Because you only see the melt at 9% MgO from the most primitive one.
Yeah. So I'm going to choose, for this calculation, a glass which, both in the calculation and if I chose to do the experiment, is primitive enough that it has only fractionated olivine. You don't always have that.
Okay, and then
right?
Other question, why do we observe glasses, natural melts, that just at the moment where they start crystallizing something else than olivine? You know what I mean? I mean, we don't observe anything that is just olivine saturated. We observe melts that are olivine plus plagioclase or olivine plus pyroxene saturated. Am I correct?
Not always. You can find olivine saturated glasses if you're lucky. Also, you can find them as melt inclusions in olivine.
So uncommon?
Not so common. Why are they not common? They are not common probably because the surface of the Earth is cold and only hot liquids are only fractionating olivine. It's hard for them to get all the way to the surface. But the other reason is, if you look at the evolution of the density of liquids, it goes down during olivine fractionation. It reaches a minimum, and then it starts to go up again when you fractionate plagioclase. So there's a sort of minimum density right around the appearance of plagioclase, which is thought by some to control where you are likely to erupt. Some combination of temperature, density, and tectonic stresses control when eruptions happen. It's a complicated question. Yeah.
So I have a question about the phase mass
Mm-hmm.
data file. Is that the values in there showing like the rate of crystallization, or not the total mass crystallized, but the
Yes.
rate of crystallization?
For a fractional calculation, we lowered the temperature, we calculated equilibrium, we got an increment of crystallization, we output to that file, and then we removed those solids to a separate reservoir, and then we lowered the temperature again. So what you are seeing there is the incremental mass that came out in that 1 degree step. Okay? You can go and add those up to get the total mass of all the fractionated solids.
So I'm just adding olivine to the melt.
Mm-hmm.
So if I just assume KD,
Yes. So
I
that,
can do it myself.
yes,
Not you.
but how do you know the KD is right?
How much do you vary the KD?
I don't. The code does it for me, right? It's a thermodynamic calculation that predicts a KD, and it's one of the things you can do at the end of this calculation is go and see how the KD behaves. If the code has been well calibrated and behaves the way we want it to, then KD will be about 0.3 and will increase slightly as we go to very Magnesian compositions, and that's what it does. It makes a good prediction, but it's a prediction. I didn't have to arbitrarily choose how I think KD behaves.
What's the best way to get a latent heat release during incremental?
So the code outputs the enthalpy at every step. So I just take the difference in enthalpies, right? You've got to be careful to define precisely in multi-component systems what you mean by latent heat, right? In single component systems, it's easy to define things like latent heat. At a given pressure, there's one melting temperature. I have the solid in equilibrium with the liquid at equal temperature. They each have a certain molar or specific enthalpy. I take the difference between them, bang. In a multi-component system, at any given pressure and temperature, I have a liquid of one composition, with a solid of different composition. They each have an enthalpy, but is that difference the enthalpy that I'm interested in? Or am I interested in, if I change the temperature by 1 degree, and I subtract out the specific heat of all of the phases, and I see how much the enthalpy changed, is that the enthalpy of fusion? Well, that's a superposition over changing some solid into liquid and changing the composition of all the solids and changing the composition of the liquid, right? The incremental enthalpy of fusion is not necessarily equal to the bulk enthalpy of fusion. And you need to make sure you know which one of those things you want. all of that information is present in the output because we're doing this using thermodynamics, and so at every step we know not just which phases are present and their composition, but their entropy, their enthalpy, their Gibbs energy, their heat capacity, their thermal expansion coefficient. So yeah, that stuff is there. It's just you need to think hard about what you mean by quantities like enthalpy of fusion. It seems like a simple thing, but in multi-component systems, it's not necessarily simple. Okay, let's look at the reverse fractionation calculation. So I'm going to look at the setup file, reverse fractional crystallization.txt. And we will see it is slightly different. Oops, what did I do wrong? Oh, I'm in example 1. Go up a level. There we go. Okay, so this calculation is still a Melts calculation. It is still an isobaric calculation. Okay. It is still a fractional calculation, not really, but it doesn't matter. Okay, and now we defined this one here, AlphaMelts fractionate target. We made it true. Okay, so that means we're turning on a calculation that's going to look for fractionation either forwards or backwards to a certain place instead of just lowering the temperature as we go. And you can define either a magnesium oxide target, such as 8 weight % MgO after Klein and Langmuir, or a magnesium number target that you think represents equilibrium with some Mantle olivines, say. So we've defined AlphaMelts fractionate target true, and we've defined AlphaMelts magnesium number target as 76.7, which is pretty primitive, okay? But in equilibrium, that's in equilibrium with about a Forsterite 92 olivine, okay? So by turning those on, we've changed the behavior of the code, right? It's not just going to step down in 1 degree steps like it did before. It's going to search. It's going to search along the olivine control line or any liquidus phase control line for a liquid that has a magnesium number of 76.7. And I'm going to do this calculation on the file ojp.melts, which is a particular glass dredged from the Ontong Java Plateau, which is a large igneous province in the Southwest Pacific. Okay? It's, again, quite a primitive glass. It's got almost 10% MgO. Okay? So it shouldn't be surprising that this is on the olivine control line. Okay? And in this case, the FO2 buffer is set to none. So this calculation will be closed system. It will start from whatever amount of ferric iron and ferrous iron you put in. This happens to be close to the QFM buffer to begin with. Okay? And it's not going to worry about FO2, which is going to save us some time. Okay, so this time we're going to run the calculation with the same command as before, except we're going to put the output in example 2, and we're going to use the setup file reverse fractional crystallization.txt. Okay, and it gives you all the usual garbage at the beginning. You can check that it correctly found. You can try to check that it did read in those environment variables. Okay, so we gave it the right file. It recognized it. So you'll always start with menu option 1. ojp.melts is our input file. It echoes it back to us, so we found it. Okay. Okay, now we actually want to start this calculation from the liquidus. Okay. We don't know a priori where the liquidus is. So right now it's at 1200 degrees and 1 bar. So if I just do a single calculation with a superliquidus initial guess, choice 3, option 1, it calculates, and it adds olivine, feldspar, and spinel, okay, a lot of them, and we only have 87% liquid left. 1200 degrees is well below the liquidus. So this is not where we want to start our incremental olivine addition calculation. It's too low a temperature. Okay, now you could manually go back and forth and say, twiddle the starting temperature, raise it, do the calculation, see what you get, etc. Or we can automate that. Okay? And this is the one example I'm going to show you today a very handy feature called phase diagram mode. Okay? Phase diagram mode is set up to automatically track along the appearance or disappearance of a phase through pressure-temperature space so that you can build up phase diagrams, such as the solidus, the liquidus, the disappearance of clinopyroxene, the appearance of garnet, whatever. We can use that to find the boundary where all the other solid phases disappear. So we say option 10, turn phase diagram mode on, which is give it a 1. Okay, now we're in phase diagram mode. So now we do a single calculation, and it says, since phase diagram mode is on, what phase do I want to track the boundary of? I want to track liquid. What melt contour do I want to find? Well, I'm going to want to find, let's say, melt fraction by mass, that's option 1, at a value of 1.0. Melt fraction of 1.0, that's the liquidus. And one more question, do I want to use the special monotonic search for troublesome phases or the quick search? The quick search will work fine. Search done. So it found that at 1233.398438 degrees, I'm above the liquidus. And happily, I can see that the last phase that was going in, out, in, out, in, out as it was zooming in on that temperature was in fact olivine. So olivine's the liquidus phase. Okay. Now I'm going to turn phase diagram mode off. Option 10, off. Okay. So now I'm set up. I have my liquid at the liquidus, and I can start the reverse fractionation calculation, which is option 4 in this case, to execute. And we'll watch it go. And this is not quite as fast as the other one, still pretty fast. Okay. So what it's doing is lowering the temperature a little bit to get the liquidus phase to appear so we can see what the liquidus phase is. Then it's adding a gram of it, okay? And then it's raising the temperature until it disappears, and then lowering the temperature a little bit to get it back in, and it's continuing that. And if we watch right here, this number that's zipping by, 13.9, 14, 14.2, 14.4, 14.6, that's MgO going up as we add more and more olivine, okay? And it is going to continue until we get to a magnesium number of whatever we said, 76.7. Okay, so it got there. And we started with 100 grams of liquid. Now we have 124 grams of liquid. So we can see that in order to get this thing from the fractionated composition all the way back up, we had to assimilate 24% olivine. Okay? And we went from the observed MgO, which was 9.9, up to 17. Okay, 17% MgO is a very primitive liquid, but this thing is a large igneous province. It's not surprising that it was hot and it had high MgO primary liquids. Okay, so again, the output files are all automatically saved. You don't have to do anything at this point. You can just quit. And in directory example 2 is all the output from that calculation. Okay. To save time, I ran that calculation and imported the output into Excel and just plotted. Doesn't really fit on the screen very well. This is FeO versus MgO. And these contours are constant magnesium number from 67 up to 78. And this is our olivine control line. Okay, as we added olivine, we went back up to higher MgO. The FeO doesn't change very much. In fact, it turns over and starts to go down as you add very magnesium olivine. Okay, and this is where we got back to, right? So, like Ananya said, there's nothing to this calculation except that it is able to predict the K sub big D, the iron-magnesium distribution, between liquid and olivine as a function of pressure, temperature, composition, and FO2, okay? And go back up as far as you want it to go, okay? And this particular composition, OJP, is also in the PriMelt2 spreadsheet, which is another method of doing this calculation that has a parameterization of KD, and you could go and compare these results. you would find that this one got up to 17.0% MgO, and PriMelt predicts like 16.8% MgO. They're quite similar. Okay. With the time that remains us, I want to start a melting calculation. That's the other thing that you might want to do with AlphaMelts. Instead of crystallizing, you might want to melt. So let's look at isentropic melt continuous.txt. Okay. So here's our setup file, and let's look at the differences. Now we're doing P-melts. This is a high-pressure calculation. We're going to use P-melts. It'll be more accurate than melts. We're still using Celsius output. AlphaMelts mode is no longer isobaric. Now it's isentropic. We can talk at length later about why we use isentropic as an approximation for decompression melting of the mantle. Okay? But the point is, we're going to incrementally calculate equilibrium, lower the pressure at constant entropy, recalculate equilibrium, which will output a temperature. We are not going to assume a PT path. The PT path will be obtained from the calculation. Okay? We're going to go in 100 bar steps, negative 100, because we're going to start at high pressure and come down. So AlphaMelts delta P matters. Delta T doesn't matter anymore. It's going to be implicit. Okay? Now, by default, AlphaMelts min P is always set to 10,000 bars for P-melts calculations, because you're not really supposed to use P-melts below 10,000 bars. But I'm going to ask you all to set aside caution and cheat, and before you do this calculation, change this to, 1 bar. Okay, because I want to do decompression melting of my mantle, and I want to go from the solidus all the way to the base of the crust. But I don't know where the base of the crust is yet, because I haven't done the melting calculation. I don't know how much crust I'm going to get. So I'm going to run it all the way to 1 bar, and then there is a part of the code which will extract the melt and solve the problem of where is the MOHO going to be, and stop the melting at that level. Okay? So we're going to throw caution to the wind. We're going to calculate all the way down to 1 bar. Okay? All right, the other important things that are set here to control the behavior of the code to do the calculation that we want are AlphaMelts continuous melting set to true. Okay, what's continuous melting? Continuous melting is code for anything in between perfect equilibrium melting, where you never extract the melt and it just accumulates, and perfect fractional melting, where you extract all the melt as if you had an infinitely strong magic straw to suck it out. Okay, continuous melting is anything in between, and the particular continuous melting calculation we will do, we'll use AlphaMelts min F of 0.005, meaning up to 0.5% melting, it will be batch melting. When we get past 0.5% melting, we will extract any melt above 0.5% by mass. Okay? We will always leave 0.5% by mass in the residue. This is thought to be a plausible approximation to the way the mantle actually works, given that melt extraction is efficient but not perfectly efficient, and it becomes less efficient as the melt fraction goes down. And if Uli were here, he could tell us what the correct value of min F is, perhaps in his experiments, but we're going to set it to 0.5%. It's a good number. It gives you the right trace element behavior. The people who actually study melt migration who are sitting in the back of the room are not freaking out. Okay, we'll just keep it there. There's another version here which is commented out, where instead of having a particular fixed residual melt fraction, you can extract some percentage of the melt at each step as a different approximation to continuous melting. Okay? And we're not going to turn anything else on yet at this point. Okay. Good. So I made a change, so I'm going to exit with :X. Okay, we're also going to look at our input file, which is Workman Heart, WH, DMM, depleted Morb mantle, no KP, we don't want kitchen patrol, .melts. And this is our starting file. It's the depleted Morb mantle of Workman and Hart, the one with the fixed sodium that actually gives you a reasonable Morb. Okay. The way that this differs from Workman and Hart's major element composition is that I have removed potassium and phosphorus. Okay? I've done this for a very excellent reason, which is in mantle assemblages, in the absence of water, Melts doesn't know where to put potassium or phosphorus other than in the liquid. It doesn't know what solid can host them. Okay? We don't really want apatite in our mantle. We don't have any water, so we can't make a mica or a potassium richterite or an amphibole or something, and we don't want feldspar, so we don't know where to put potassium, which means if we include even a tiny amount of potassium, this assemblage will not have a solidus. We can't freeze it. We will have melt down to arbitrarily low temperature. This behavior is bad. We want to have a solidus. We don't really care about the phase equilibria consequences of just a little bit of potassium and phosphorus for these purposes, so I've removed them. In the next calculation, which we won't have time for today, but you can do later, I put them in as trace elements. I just said there's 50 parts per million potassium as a trace element, and that's pretty much just as good for the melting part of the problem. Okay? So that's just a warning. If you're going to do melting calculations, you don't want any of these really incompatible components in the major element reservoir. Okay? Apart from that, this is just a perfectly happy, sort of mildly depleted peridotite composition, right?
Well, you have an initial and final pressure in that line.
Yeah.
How does that interact with what was set up in the fixed heat time?
AlphaMelts does not look at the final pressure, increment pressure, final temperature, or dPdt lines of these files at all. They are irrelevant. They are a holdover from the graphical user interface. Okay? Note that I have set the FO2 buffer to none, okay, but I have preset the composition to have a certain amount of Fe2O3 in it. Okay? The reason I have FO2 buffer set to none is an interesting but somewhat obscure reason. Okay? We're going to be doing an isentropic calculation, conserving entropy. The way that you buffer FO2 is by exchanging oxygen with the environment. If I exchange oxygen with the environment at constant entropy, that means I'm talking to a reservoir of pure crystalline oxygen at absolute zero, because it has no entropy. Well, I don't want to do that, right? So I could do a more complicated calculation where I go back and forth between steps at constant entropy and steps where I exchange oxygen with the environment to get a new reference entropy, but look, my observation is that if you set up a peridotite close to QFM or QFM minus a couple, or even QFM plus 1, and then you decompress it, it will be well behaved. It will stay close to the oxygen buffer you put it on, and that's basically the spinels and the pyroxenes talk to each other. Okay? So we're not going to buffer the FO2 during the melting calculation. You have to buffer it during fractionation calculations, or you get weird answers. Okay. So we are going to run the code. We're going to put our output in example 3. This is going to be isentropic melt continuous.txt. I always like to look back and check that I really did see my environment variables. Yes, I did. Okay. First thing you always do is read in the input file, which is wh-dmm nokp.melts. It read it. Okay, now, what condition are we going to start from? Okay. I want to calculate, in this case, the exercise is to do the decompression continuous melting path of this peridotite for a mantle with a potential temperature of 1350 degrees C, which is sort of the number that most of us think normal Morb mantle has. Okay, what is potential temperature? It is the temperature that you would get if you took your subsolidus peridotite and you brought it to 1 bar pressure without allowing it to melt, and you equilibrated it there. Metastable against melting, okay? And it gave you a temperature of 1350. Well, you know what? We can do that calculation, okay? So we can have a rigorous definition of potential temperature. Here is how we're going to do it. We are going to say, take us to a starting composition of 1350 degrees C and 1 bar pressure. Turn off the liquid. Number 9, turn liquid on and off. So suppress liquid. Okay, so now we're going to do a Gibbs energy minimization. Sorry, 1350 degrees C and 1 bar with the liquid turned off. Okay? So the code is perfectly capable of doing metastable calculations where even though the equilibrium state will be partially molten, we're not going to let it add liquid to the assemblage. Okay? So now, with liquid turned off, we do a single calculation. And now we'd better use the subsolidus initial guess. Can't really go using the superliquidus initial guess with liquid turned off. So option 0. Okay? And now it asks for a list of phases to include in the subsolidus initial guess. Okay? And it will work best if I tell it to use olivine and I tell it to use feldspar because I'm at 1 bar. Okay? It always adds 2 pyroxenes. That's just the way it works. And it will see that there's chromium in the calculation, and so it has to add spinel. It will do that for us. I don't have to. So I'm just going to say olivine and feldspar. X when you're done. Bang, it runs. So the initial guess calculation, okay, added clinopyroxene, orthopyroxene, and spinel. It made an initial guess of this plagioclase plus spinel peridotite composition. Then it equilibrated it. And it turns out that metastably at high temperature, at 1 bar pressure, orthopyroxene drops out. And this is your equilibrated peridotite composition, whatever. Doesn't matter. The point is, I did this calculation, and so the code knows the entropy at this point. Okay? And so now I say, option 7, impose the initial entropy, enthalpy, or volume. Okay? And this is the entropy, 257.287 joules per Kelvin. Just some arbitrary number to you guys. Okay? I've done this enough that I recognize that number, and I know that it's a reasonable temperature for a reasonable entropy for this potential temperature. And so now I'm going to type the new reference entropy. The reference entropy is not set. The current entropy is this. I want to set the reference entropy to equal the current entropy, which means I put in a negative number here, just as a flag. Okay, so now if I say 7 again, it says the reference entropy is the same as the current entropy. Okay? So now I can turn liquid back on. Option 9, turn liquid on. Okay? And now if I equilibrate again, just so you see what it's like, okay? So I'm still at 1350 degrees C and 1 bar, okay? Well, I was at 1350 degrees C and 1 bar, metastably, but I turned liquid on, and I recalculated at the same entropy, and what happened was I made 27 grams of liquid, and the system cooled itself 77 degrees. Does that make sense? Right? Constant entropy. I made liquid. It's a high entropy phase. Where did I get the entropy from? I cooled the system down. Okay? And so this would be the final end state of a decompression equilibrium melting calculation at this potential temperature. It would end up with a dunite residue and 27 grams of liquid. Okay? That's not really what I want to do. I want to go down below the solidus, and I've checked this calculation. If I try to do it in a single step, it's going to crash on me. So I'm going to do it in 2 steps. It doesn't matter what temperature I say. I'm going to say option 2, go to 10,000 bars first, equilibrate, option 3. Okay, so now this is the same entropy, still the same bulk composition at 10,000 bars. It obtained a new temperature, okay, getting close to the potential temperature, just coincidentally. We're down to 10 grams of liquid. Our pyroxenes came back in. We're on our way there. And then I'm going to do it one more time. Change the calculation. Doesn't matter what temperature I say. Go to 20,000 bars and equilibrate. And now it checked whether garnet was going to come in. The answer is no at this pressure. Dropped the liquid. And now I have a subsolidus peridotite at 20,000 bars at some temperature that happens to correspond to the potential temperature of 1350. So I've set myself up. I'm all ready. Okay? And now if I execute, it's going to progressively go down in 100 bar steps. Every 100 bars, if the liquid is more than half a weight %, it's going to extract the extra. Okay, so this number is staying close to half a weight %. Okay? Until it gets all the way down to 1 bar. Okay? And you see, doing fractional crystallization instead of equilibrium crystallization, now I still have some residual orthopyroxene. which gets back to that melt focusing thing I talked about at the beginning. Okay? So we just did decompression melting of the mantle at constant entropy at a potential temperature of 1350 all the way from the solidus to the surface, okay, in seconds, which is awesome. Now, I'm going to use option 16 here. And I'm going to do one more thing, and then I'm going to let you all go. Okay? I'm going to calculate, use option 16, the pressure integral, simple rectangle rule. I'm going to make a file called integratedtable.txt, and I'm not going to write out input files. And I'm going to let that go, and then I'm going to quit. Okay, so let me show you what that file I just wrote is, because it's very useful. So we'll go to example 3. Now, in addition to the 8 output files that you always get, we got that extra one I made, integratedtable.txt. Okay? And the exercises file includes a summary of what every entry in this table means. But let me just say in general, okay, when we're trying to model mid-ocean ridges, we think of a triangular melting regime, okay, below the crust. We think of parcels of mantle flowing in and through the melting regime. We think of them generating melt at every point along those streamlines, okay? And we think of taking all those melts and mixing them up to make the primary melt that's going to come out, okay? And that amounts to, if you just calculate the streamline that goes up the middle, we're going to be integrating the melt along that streamline, but then we're going to be integrating again along a set of streamlines that don't get all the way up to the top. So there's a formalism for taking a double integral over the liquid compositions to yield the estimate of the primary aggregate liquid. Okay, and this formalism goes back to the late 80s to Klein and Langmuir and Mackenzie and Bickel. Okay, it's an analytical way for any corner flow that goes through a triangular melting regime to estimate the bulk liquid that comes out the top. Okay, and this file does that. So we just calculated one streamline straight up the middle, all the way to 1 bar. Okay, and when we set option 16 and we calculated this integrated output file, it does that double integration, and here's what it says. Okay, it says this third number in the first row, ZC base, is the crustal thickness in kilometers, and it is 6.06 kilometers, okay, which confirms that for this source, for this model of melting, for this potential temperature, we made something that could be a plausible oceanic crust. Okay? The mean extent of melting is 0.094. That's FB at the base of the crust. Okay? The interesting number here, P sub C, 1557 bars, that's the pressure at the base of the crust. So what the code did was it compared, if we stopped the melting calculation at a certain pressure, to what pressure of melt we would have extracted up to that point and piled up on top, and it found where those things agree. It found that if we stopped melting at 1557 bars, that we would have 1557 bars worth of mass of crust on top of us. That's how we find the base of the crust. Okay? The mean pressure of melt extraction, that's the fourth number here, is 10,000 bars or so. Okay? And going further along here to the entry that starts at silica 2D, we have the aggregate primary liquid for a two-dimensional melting regime calculated there. Okay? And so what you might want to do is, having calculated the aggregate primary liquid, you might want to turn around and fractionate that liquid with melts, okay, because this aggregate primary liquid has 12.7% MgO. It's more primitive than typical erupted morbs. And that last option that I said no to was, do I want to output melts files when I do the integration? I said no, but if I said yes, it would automatically take this integrated liquid composition file and format it as a melts input file that I could then take and run the fractional crystallization calculation on. The rest of this table is a tribute to a paper by Shen and Forsyth, 1995, who said at slow spreading rates, you don't melt all the way to the base of the crust. You cut off the melting at some depth due to conduction, and you get a trapezoidal melting regime. Okay? And so all of these lines here show what the aggregate liquid would be if you stopped melting at that pressure, all the way down to the bottom. Okay? That's a lot of information. Okay? And the basic point is, for this particular peridotite source, for this particular potential temperature, 1350, for the model of continuous melting in a two-dimensional passive flow regime, we predict 6 kilometers of oceanic crust with a composition which is a very good model for a primitive morb. We could fractionate it to get compositions that look like EPR glasses. Everything seems to be super happy. Okay? We actually seem to know how to go from what we think is the peridotite source in the mantle to what we think is the oceanic crust. They all agree, and we did it all with thermodynamics with no direct input from petrology melting experiments, except insofar as they went into calibrating the thermodynamic model. Okay? So there are some more exercises on the virtual box, which you can sit here and run now or at leisure. Okay? The next one is a pH melts calculation, where we repeat this calculation, but we add 150 parts per million water to the source, and we see how that changes things. Okay? There's some other calculations in there. I think they're documented in the handout. But that's the quick version. All right? If you're really interested, okay, I'm going to announce to you guys now before I announce to the public. The week before AGU this December, we're going to have a 4-day melts camp at Caltech, where you'll get the detailed version of the last 104 minutes. All right? Thanks, everybody.
So I managed to make 0 kilometers of ocean crossing. Know exactly how to
Let's see.
How we put it. No, I put it.
Oh.
I think I must have input the pressures wrong. I must have made choices too quickly when we were talking. So I ended up with the first 4 numbers were 0, and then 48.
That's the answer. Right.
I
have a very quick question.
Probably you didn't extract any melt, right? When you're doing it, when you're doing a continuous melting calculation, only the liquids above min F, the ones that get extracted, those are the only ones that show up here, right? So we started melting at 20,000 bars or something, but there's no entries here until 18,000 because that's where melt started to get extracted.
So just in terms, when you say that you have this batch processing thing, is that like the steps like, turning on 3, 4,
yeah,
doing
exactly.
Stuff? So these are the ones that can be automated in batch.
Everything that I typed interactively.
Because I made a typo at the end, so of course the thing crashed, and I was like,
right.
There's no way I can reproduce all of this.
So
without having my checklist. So
yes. So the instructions that we didn't read, but they're on the wiki. Step through these step by step.
Yeah.
And if you want, I have batch files that go with each of these exercises. But if I just feed you the batch and it goes, you're not learning about how to choose what calculation to do.
Right.
But yeah, the batch files are nice because you do screw up at the end sometimes, or the code doesn't go and you have to, So it's nice to have that choice.
No, I'm just thinking in terms of automatizing things. Like you were saying, you have these libraries that are going to come out. But
And so, with the code as it stands, if you want to imagine embedding it in something else, right, you can do it with file passing, right? You can have a setup file. You can write a melts input file. You can write a batch file. You can say go. It'll return the output files. You can read them in. Okay, that's what Laura's code that did, right? It was all through files that basically AlphaMelts talked to Gypsum. Okay, we are getting close to having the libAlphaMelts interface ready to go, where you can, set all of these things through calls from MATLAB or from some other environment and embed it in your calculation, whatever your calculation is. The hard part, whenever you embed something, is it has to give an answer every time. Absolutely, failure is not allowed. Because if you're going to be running 1 million calculations, one of them is going to bomb, right?
Yeah, and it's like the things you were saying, like you have to make to map out the temperature in 2 steps, like you wouldn't know that a priori.
Right. Yes. So.
However, here that 2-step, even with a not so weird composition, that was something you have to know.
Yeah. So that was a lot of the reason why Laura's project was so hard.
Yeah.
Is we had to either make it globally convergent or glue on a solver for every possible failure.
And of course, in our case, it was feeding back directly into the Mantle convection code.
Right.
Which
I just wanted to take the solid or even the liquid and feed it into the test. That's why I was asking about the phases. I was curious with the phase assemblage.
Yeah. So
residual solids would look.
So it's all there.
Yes.
So for example, if we look at solid comp table.text gives us the bulk composition of the residues, and so we can watch. Okay, we started out with ordinary fertile peridotite, and as we melt, we'll see sodium going down. We'll see here's MgO going up, right? We'll see chromium going up. We'll see aluminum going down. We'll see titanium going down. We'll see silica going. It can go either way, but it goes down in this case. And that continues. So we come all the way to the sodium went to 0 at some point, and we dropped it. So we ended up with 47% MgO, 42% silica, 0.2% alumina. This is a very depleted Hartsbergite here. Quite a bit of chromium, et cetera. So that's all. So the oxides are all there, and then.
I wanted to understand how to read that phase.
We'll first look at phase mass table, which is pretty easy. Those are the masses of the phases. We started out with fertile lertzolite. We ended up CPX. CPX went to 0 at 5.4 kilobars, and because it's fractional melting, we end up with still some orthopyroxene with our olivine, with our spinel.
Right. Okay, so that's how I read it. Okay.
Right, and then to look at the phase compositions. Those are here in phase main table, which is a little bit wide, but these are the liquid compositions restated with a little more thermodynamic information. Here's the clinopyroxenes, so it gives you the molar formula if you like reading molar formulas, and then it gives you the composition of the phase in weight percent. And some of those are easier to read than others. Okay, here's the olivine, right? It's Fo89, so 40% silica, 48% MgO. Iron, nickel, manganese, calcium.
Okay, great.
And
And that for the project we were talking about.